So one of the major questions facing computer vision today is that we're seeing so much exciting progress in computer vision benchmark data sets, and we're also seeing a lot of impressive results published in papers. Well, how well does this translate to some of the ambitious real-world applications that's often described as the potential of computer vision, such as autonomous driving or AI clinician assistance? One recent situation that put computer vision to the test was the COVID-19 pandemic. And so this is something that affected all of us, and it also involved a lot of visual data. We had X-rays and CT scans of the chest. And so it was actually something that there were a lot of efforts initiated in trying to see how we could use computer vision to assist clinicians. And so there are a lot of applications, particularly around developing models to try and diagnose or predict COVID severity, and for uses such as hospital worklist triaging or predicting ICU admission. So how well did we do? There were hundreds of works that were published, and there's been a number of works that have performed sort of a survey of some of these works that were published during the peak of the pandemic. And what a lot of these works found was that, unfortunately, that computer vision models largely didn't really live up to the hype, and that of many of the models that were developed, only a few of them were really fit for deployment in real-world settings. And so what went wrong? Well, there's a number of reasons. One of these is that many of the efforts for developing computer vision for COVID were largely tackling tasks that were chosen based on ease of achieving that task and not necessarily on actual utility. And so, for example, radiology societies have questioned the utility of using imaging alone to diagnose COVID. However, a lot of works focused on COVID screening solely from images. And this is likely due to the relative ease of obtaining data sets containing medical images paired with COVID labels. And so these works sort of focused on this as opposed to more multimodal models that had been recommended, and largely for these reasons of convenience. And at the same time, there are also many models that chose to evaluate the models or tasks based primarily on the outcomes that were also easiest to obtain. And so, for example, COVID positive or COVID negative, as opposed to what might actually be most useful to clinicians. And so, for example, for clinicians that were treating many COVID patients overloading the hospitals, that models that could help more in terms of improving patient outcomes were something that potentially had greater utility. So a second reason why computer vision didn't have as much measurable positive impact during the pandemic was that a lot of these models were found to be not able to be necessarily trustable for real world use. And so this is related to the theme of this workshop because a lack of explainability was a big factor in all of this. And so there were a lot of models that were kind of hastily developed during the pandemic, and there were a lot of biases or spurious correlations that existed in these. But for the most part, many of the risks of this were either too high or too unknown to be able to deploy these in real world settings. And so some retrospective works have looked at some of these models and found various types of spurious correlations. So for example, models that would pick up on imaging markers in X-rays. And so here you can see on the left an example of this, and picking up on these markers that distinguished hospitals that had different COVID prevalence levels instead of the actual disease. Or another example on the right is that some models could also pick up on the fact that some patients that had more severe COVID would be imaged lying down because of their disease as opposed to upright. And so these are examples of some of the failure modes that happened for computer vision during COVID. And I think it gives a compelling real world example of some of the need for explainability to help help understand models and to develop models that can be trustworthy for real world deployment. Fortunately, there's a lot of exciting work ongoing in explainable computer vision, and one of the major directions is around vision language models for different uses such as explaining predictions, explaining neurons, or explaining mistakes. One component of many of these models is learning a cross-modal representation space. And so I'd like to talk now about some of our ongoing work, both in learning this type of representation space in the context of medical imaging, and then secondly, more generally on studying some of the properties of this representation space, and in particular, modality gap. So in the context of medical imaging, in this domain, it's relatively expensive to be able to manually annotate radiology images. But at the same time, we have actually a lot of paired medical images with free text reports. And so this gives us data with which we can use to learn cross-modal representation spaces. Existing work has started to explore this direction using contrastive learning. And one example of this is the convert model, which was an approach that learned an image encoder and text encoder for radiology reports with paired text reports, radiology images with paired text reports. They learned the global representations from each input modality where they used a standard contrastive learning objective to maximize agreement between paired global image and text representations. However, learning global representations can be limiting, particularly in medical images, where the visual pathology often occupies a very small region of the image. And so this leads to the question of whether this contrastive pre-training can be improved if we also consider more local representations between regions of the image and text. And so this is work that was conducted with my student Mars Huang, together with Liu Shen and Matt Lundgren. And in this work, we looked at trying to simultaneously learn both global and local representations for medical images with paired text. And so the model works as follows. We have radiology images and text reports. And for each of these, we have a respective image encoder and text encoder. And so given these, with the image encoder being just a resonant model and the text encoder here being a transformer-based BERT model to handle the longer text inputs that we have, here we can first take the global features that are output by each of these, and we can maximize a global contrastive loss. That's just the standard formulation that I also showed earlier with the convert model. But now we would like to simultaneously learn local representations for both the images and text. And so specifically what we do is we can take image region features and word level features from earlier in the respective encoders before they have been aggregated. And we can compute a similarity matrix for every local image region with every word. And we can then normalize these values in the similarity matrix to produce an attention weighting representing the attention given to each image region for each word. And we can then use this to compute an attention weighted image representation for each word by weighting and aggregating the image region features according to the attention from the word. And then finally, we can compute a local feature-based similarity score between a full image and text by aggregating the similarities between words and the attention-weighted image representations. And we can use this to compute a second localized contrastive loss that still follows the standard contrastive loss formulation, but now operates based on these localized representations. And so our full representation learning objective consists of both the global loss and the local loss that are optimized jointly. So after performing this contrastive learning, the learned global and local representations can be used for different downstream tasks. And so we can take the image embeddings from the trained image encoder and utilize these for tasks like retrieval, classification, and segmentation. And so what we found here is that the local representations contained meaningful information that was able to enhance the global representations for these different tasks. And I won't go into the details of this today, but we basically presentations in a straightforward manner, and we're able to show stronger performance compared to previous works across these tasks. The learned local representations and attention weightings also allow us to explore interpreting where in an image a model is paying attention to for a given word. So here we can visualize some of these, and you can see, for example, that the attention weight for the word effusion is overlaying regions of the image with plural effusion, and we can see the same for these other medical conditions here. And so what we can see here is that by performing this global local contrastive learning, that we're able to basically, without having the classification labels for these, still learn attention weightings that sort of correspond appropriately for words with regions in the image. So now going a step further, we can also obtain explainability from the cross-modal representation space that's learned. And so, for example, we can take a set of fine-grained text prompts that describe various visual pathologies that can exist, subtypes of visual pathologies that can exist. And using this, we can use the text encoder to map this into the joint representation space, and we can compare similarity with the embeddings from the image encoder, and to be able to find the descriptions that most closely match the image embeddings. So now, as we get into thinking about these relationships between images and text in the learned representation spaces, this gets to this question of well, how well aligned are actually these learned cross-modal representation spaces? And so, so this is work that a direction that we're exploring in work that is together with my student Yuhui Zhang, as well as Weixing Liang, Youngchan Kwon, and James Zhu. And so in this work, we studied sort of the alignment between image and text representations in the representation space, which here we refer to as the modality gap. So what we wanted to do is we wanted to understand the structure of the learned cross-modal representations that are resulting from multimodal contrastive learning. And so we started by focusing on a popular model for this task, the CLIP model. And so what we did was we took pre-trained, the trained encoders from CLIP for both images and text, and then took 5,000 image and text captions from the COCO captions dataset and embedded these using these encoders. And so here you can see a visualization that shows some of the modality gap that results, where here we have image and text representations forming these distinct clusters, even though they correspond to the paired data. We also repeated this experiment across different contrastive learning models and data sets, here including a video clip, as well as the convert medical image and text model that I discussed earlier. And we can see that the modality gap is pervasive across all of these scenarios. And so what this implies is that the embedding space for each encoder is restricted to a narrow cone. And we can see that this is the case when we plot inter-image and inter-text cosine similarities. We can see sort of all the positive cosine similarities that exist between pairs of images and pairs of text. And then going further, we can see that this cone effect is a general phenomenon for deep neural networks. And so here, for example, I'm showing 3 different pre-trained models across images and text. And here we're plotting the distribution of cosine similarities between output embeddings from these encoders. And we can see that they all, this is from this distribution, we can see that they all have significantly positive average cosine similarities that indicate this cone effect. So this has been observed before, including for language representations from language models. And one common explanation is that this can arise from the optimization process, for example, due to the imbalanced distribution of word frequencies. But what we did here was also then repeat this with now the models are randomly initialized with random weights, and still using the real data, and we can see that this cone effect still exists, even a little bit more strongly here. And so this indicates that the modality gap is actually born at the initialization and exists at the beginning before we start the contrastive training. And so here you can see also additional visualizations showing this, where the bottom row is showing the same type of modality gap now with random weight initializations. And then here we showed now the same thing, but with the input being random noise instead of the real data. And so you can see that again, we still have this effect. And so this suggests that it's not due to the data distribution, but is a more general inductive bias for these deep neural networks. The plots here now show that different random initializations create different cones. So here we have, for these different models, the same encoder for each one and the same input data, but we just have different random initializations just from different random seeds. And so we can see here that each random initialization forms a distinct cone. And so this sort of gives some intuition for the modality gap at initialization, where since we have an image and a text encoder, we basically therefore already have these two different cones at the beginning. Okay, so we've seen so far that we have the modality gap that's born at initialization due to the cone effect of having these two encoders. So now what happens during contrastive learning? And what we find is that during the process of contrastive learning, this preserves the modality gap and also can further encourage it slightly. So here I'm showing basically the modality gap for the CLIP model using the standard contrastive learning objective, and also with the low final temperature of CLIP. And we can see here that the final learn model exhibits this gap. And then we investigated what happens here if we actually try to close this modality gap by shifting the features along the axis, the yellow arrow here, connecting the centroid of the image and the text modalities. And so the plot on the right is showing on the x-axis the distance between the modalities as we vary this distance, and then showing the validation loss here. And so what we can see here is that with the temperature of final temperature of CLIP, that that the actual optimal performance occurs when there is a modality gap, and then as we shift to try to close this gap, the loss will increase, and then if we keep on going further and sort of cross shift to the other side past zero, then we can see another local minimum at that point. And so this shows kind of the repulsive structure that exists here. So now how does temperature affect this optimal gap? And so we explored this further by performing fine tuning of the CLIP model on the MS COCO captions data set with different temperatures. And so here you can see that as the temperature is increasing, this repulsive structure is gradually disappearing and closing the gap becomes more optimal, but the loss is also higher overall. And this shows how the gap is temperature dependent. Finally, we also looked at the relation of mismatched data to the modality gap. And so we looked at this in this simulation setting, where here we simulated image and text embeddings here on the unit sphere. And we have a pair of mismatched data that's on the far left here. And so you can see that with this mismatched data, if we then plot this loss landscape, we can reproduce the repulsive structure that we saw on the real data, right? So here the x-axis is the distance between the modalities here by varying the angle between them. And then we can further see that if we remove this mismatch, then this repulsive structure disappears. And so we can see here that the optimal performance here is with no modality gap. And so I think what this illustrates is that the presence of mismatched data is also an important factor in forming the modality gap under low temperatures. And in practice, this is a common scenario that we have in training these types of multimodal models. Okay, so what we've seen here is that the modality gap is born at initialization due to the cone effect of two encoders, and that optimization can further encourage the modality gap through mismatched training data. And so we found that in practice, the modality gap at the end can be a little bit higher than during initialization. And so finally, we also want to consider, well, what sorts of implications can this modality gap have? And so we looked first at some examples of modality gaps relationship with performance. And so here we're taking the CLIP model, and you can see the original gap from the trained CLIP model that's shown here for different data sets. And then we tried to shift and change the gap in different ways, just through this straightforward manner of closing the gap along the axis, connecting the two modalities. And so what we found is that you can get better performance through different values of the modality gap, but that there isn't a consistent pattern in what's the direction of shift that can achieve this optimal gap. And we also looked at modality gap relation with fairness. And so this is showing a zero-shot evaluation of CLIP on an evaluation set of fair face classes. And so here, in addition to the 14 fair face classes, we also added 4 non-human and 3 crime-related classes. And so these correspond to denigration biases. And so we show here on the right the percent of the top 1 predictions here that are offensive that belong to one of these non-human or crime-related classes. And so in red, you can see what's some of these biases that exist with the original gap. And then on the right-hand side in green, this is showing a different value of the modality gap. And here you can see that with this, you're able to have a lower percentage of these offensive predictions, but with little change in accuracy. And so this is just sort of very early exploratory work trying to look at some of these potential implications of the modality gap. But our work was primarily focused on studying the properties of the modality gap and as opposed to the downstream implications of it. And so I think this is a very fruitful area of potential future work on understanding what are some of the implications of this modality gap in the many applications that rely on these sorts of cross-modal representation spaces, including in explainability applications. Okay, so to conclude in this talk today, I started by discussing the tests of COVID-19 and how medical computer vision performed during COVID-19, and we found that it did not live up to the hype that we often imagine for computer vision. And one important factor of this was the inability of models to be trusted for real-world use, and of which explainability is a major factor in this. We also discussed how learning good cross-modal representation spaces are one way to enable explainability approaches. And then we talked about learning both global and local representations in the context of medical imaging. And then finally, we discussed multimodal contrastive learning and how this exhibits a modality gap that's born at initialization and then further encouraged with optimization. And so I think the implications of this is an interesting area of further study. And so with that, I'd like to thank and acknowledge the members of my group that have driven a lot of the research that I've talked about today. And I'm happy to take any questions.
Okay, maybe it's easier if the question is asked here because that microphone,
okay. Yeah.
And then so the Zoom people can also hear it.
Thank you. That was really a great talk. I'm really curious about what is the best way to produce an explanation. Say you make a diagnosis, typically you would potentially provide a sequence of reasons as to why you arrive at that diagnosis. But the records might have what the radiologist sees, but the diagnosis might be a subset of it. And so I wasn't entirely clear how the model based on text and images actually makes those predictions in a way that would actually produce an explanation in a way that that the clinician will then make a decision, right? Which is not the same as what the radiologist writes.
Yeah, thank you. So that's a great question. And I think that if you're trying to perform, let's say, learning using only the paired images and radiology reports, then you are limited in this fashion that, yes, you can try to see which parts of radiology reports that are as close as possible to a useful explanation can correspond to the image, but that's a limitation. But I think that one potential area is to address some of this is by trying to leverage more richly learned language representations across many other data sets that exist, some of which are not necessarily corresponding to those direct medical images, whether they're from the large language models, whether they are from other data sets, medical data sets that contain primarily text. And so I think that's an interesting direction to explore. I think the open question is, well, how well will those actually work? How relevant can they become for providing these explanations? And so I think that's kind of an unknown question that needs to be explored.
Okay, Dipti, is there any questions on the Zoom side?
Yes, we have one question from Pradeep. Is the variance large in modality gap directions? That is, maybe it's largely a constant offset.
Sorry, so you're saying is the variance large in the modality gap directions? So in our work, we characterize some of where the variance of the distribution comes from, and coming from sort of how the intermediate representations, the variance there comes from some of the variations in the source in the data distributions, and so we have some of that characterization that's in this work that has a preprint on arXiv, but in terms of the precise variance for these examples that we've given, I don't have that, but that would be an interesting thing to also look at.
Okay, if there are no more questions, let's thank the speaker again.
Thanks, Serena.
Okay, thank you very much. We are very grateful that you did the talk, and